Hi guys, welcome back to YouTube channel Chemistry Live UGPG. Today we are going to talk about atomic structure, CC1 paper, G1 paper, Unit 1, Lecture 3. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime, and help to learn others. So this is the syllabus for CC1 paper for BSc Chemistry students, honors students, and G1 paper for generic students. So today we are going to talk about derivation of Schrödinger wave equation for hydrogen atom in Cartesian coordinates, significance of psi and psi square, shapes of s, p, d and f orbitals, nodes or nodal planes. So in order to express mathematically the wave, so equation of wave is described. So since electron behaves like a wave, so the next step is to formulate a wave equation for the wave motion. So this is you can see this picture, this is the way how the wave travels. So if you have seen the sea beach, so you can assume the movement of a wave. So at this point here you have a node and this is called amplitude and this is the direction of propagation of wave. So psi is called wave function or amplitude function. So the Schrödinger equation is a linear partial differential equation that describes the wave function of a quantum mechanical system. So let's derive the Schrödinger wave equation. So this is the standing wave whose wavelength is lambda and A is the amplitude. So for a standing wave of wavelength lambda whose amplitude at any point along x can be described by the function fx. So we can write as d square fx by dx square equal to minus 4 pi square upon lambda square fx. So if an electron is considered as a wave which moves in only one dimension, then d square psi upon dx square equal to minus 4 pi square upon lambda square into psi. So an electron may move in three dimensions like x, y and z direction. So this becomes del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square, that is equal to minus 4 pi square upon lambda square into psi. So we can use the symbol del instead of three partial differentials. So that becomes del square psi equal to minus 4 pi square upon lambda square into psi. And we know the de Broglie relationship that lambda equal to h upon mv. So here lambda is wavelength, h equal to Planck's constant, m is the mass of electron and v is the velocity of electron. So now we can put the value of lambda. So del square psi equal to minus 4 pi square m square v square by h square into psi. So now here this is negative sign, we can take to the other side. So del square psi plus 4 pi square m square b square by h square into psi equal to 0. So this is equation number 1. And we know the total energy of the system E equal to kinetic energy plus potential energy. So kinetic energy equal to half mv square, P that is potential energy equal to V. So total energy equal to half mv square plus V. So kinetic energy half mv square equal to E minus V and V square will be 2 upon m into E minus V. So putting the value of V square in equation 1, we can get del square psi plus 8 pi square m upon h square into E minus V into psi equal to 0. So this equation 2 is known as Schrödinger wave equation. So this is the equation derived by Schrödinger. So here you can see in three Cartesian coordinates del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 8 pi square m upon s square e minus b psi equal to 0. Or we can write in terms of del square. So del square psi plus 8 pi square m upon s square e minus b psi equal to 0. So here del square equal to del square upon del x square plus del square upon del y square plus del square upon del z square, that is called Laplace operator, where x, y and z are space coordinates of the electron of x, y and z axis, where m is mass of electron, h equal to Planck's constant, E equal to total energy, that is Ke plus P, kinetic energy plus potential energy. So here B is potential energy of the electron, that is Coulombic interaction between electron and nucleus. And psi is the amplitude of wave called wave function. And del denotes partial derivative at position x, y and z. Del square psi upon del x square, that is second order derivative of psi with respect to x. So that we can rewrite as minus h cross psi square upon 2m del square plus b whole into psi equal to e psi, that is s psi equal to e psi. So this is another short form of Schrödinger wave equation. So here h cross equal to h upon 2 pi. And now let's discuss what is the significance of this Schrödinger wave equation. So if we solve the second order differential Schrödinger wave equation, some solution have a certain definite number is of significance. These significant values are called eigenvalues, and the wave function corresponds to eigenvalues are called eigenfunctions. The next is the significance of psi and psi square. So psi is the wave function, psi is the state of function and has no physical significance. It represents only amplitude, that is maximum displacement. Similarly, psi square represents probability of finding per unit volume of a particle by the function psi, or that is probability density. The next is characteristics of psi. Psi is single valued, so that means probability of finding an electron in space has one and only one value, and it is continuous. Then finite, and integration minus infinity to plus infinity psi square dv equal to 1. So that means this function should be normalized. The next is psi square. Psi square measures the probability of finding an electron of a given energy in a given region around the nucleus. So that gives the concept of atomic orbital. So what is orbital? It is defined as a three-dimensional region around the nucleus where the probability of finding an electron is maximum, is called an atomic orbital. And the eigenfunction for an electron is called an atomic orbital. So example S, P, D, F orbital, and the maximum number of electron in an orbital is 2. So let's talk about shapes of orbitals. The shapes of orbitals is defined by angular momentum quantum number L. So L can be 0, 1, 2, 3, etc. And when L equal to 0, that is S orbital, L equal to 1, P orbital, L equal to 2, D orbital, L equal to 3, that is F orbital. So when L equal to 0, M equal to also 0. So that is S orbital, so that is spherical shape. So there is only one S orbital per cell. So the size of S orbital increase in size as the value of n increases. So m equal to 0, that means only one orientation. So equal chance of finding electron density in any direction with respect to the nucleus. Similarly, when L equal to 1, so m value equal to minus 1, 0, plus 1. So that is p orbital. And a p orbital shape is dumbbell shape. So here you can see px, py and pz. So this m value minus 1, 0, plus 1. So when m equal to minus 1, that becomes pz orbital, m equal to 0, px orbital, and m equal to plus 1, py orbital. So when L equal to 2, m value becomes minus 2, minus 1, 0, plus 1, plus 2. So that represents, that means you have 5 values. So L equal to 2 means d orbital. So here in 3D we have 5 3D orbitals, dxz, dyz, dzx, dx square minus y square and dz square. And here is the shape. So dxy, dyz and dzx, their lobes are in between the axes, and that is known as T2G set of orbital. And dx square minus y square, their lobes are along the axis. And dz square, here you can see the structure, their lobes along the z axis, and here you have also one spherical shape. So this dx square minus y square and dz square, that is called EG set of orbital. Similarly, when L equal to 3, that is called F orbital. where m values -3, -2, -1, 0, +1, +2 and +3. So that means 4f have 7 orbitals. And this is the structure of f orbital, f xyz orbital. Okay, so it is a very complicated structure. And this is the contour plot for py orbital. So there you can see their lobes. So 90% of a boundary surface. Then next talk about contour diagram or nodal planes. So boundary surface diagram is a contour plot or boundary surface drawn in a space for an orbital on which the value of probability density psi square is constant. The boundary surface diagram of constant probability density is considered as a good and acceptable approximation of a shape of orbital if the boundary surface encloses the region or volume with probability density of more than 90%. And let's talk about features of a surface diagram or contour diagram. The contour plot of an orbital is independent of n, that is principal quantum number. For example, 1s, 2s, 3s, 4s up to ns, in general the shape is spherical and the shape does not depend upon the principal quantum number. Then size of contour diagram. The contour diagram of an orbital increase in size or volume with increase in principal quantum number. Next is nodes. Nodes are the region where probability of finding an electron density is typically 0. So for s orbitals you have n-1 nodes. And this kind of nodes is also observed in the diagram of a p and d and f orbitals. So to emphasize psi is a continuous function, the boundary surfaces have been extended up to nucleus. So for p orbital the electron density is 0 at the nucleus. So you can see at the center you have a node for p orbital, 2px orbital. And here you can see the boundary surface or contour diagram for py orbital. Please subscribe to our channel Chemistry Live UGPG. This is also available in the website chemistryliveugpg.com. And for class 11th and 12th students, this is the channel Foundation Chemistry AV. So this is a simple step towards e-learning, making life better. Thank you all for learning.